In this video, I'm going to be talking about the exponentiation by squaring algorithm. This algorithm helps computers calculate exponentials very quickly, and it's absolutely critical in modern cryptography, and it's also got some really cool applications that I'm going to talk about in another video. My main goal in this video is to give you an intuition for the algorithm and see how it works, and also hopefully you'll get to see how you can make your own algorithms and how you can reason about whether algorithms will be efficient or not. So during this video I'm going to be using the caret symbol to denote exponentiation. So for example, 2 to the third power equals 8. So let's begin by talking about how a computer might calculate an exponential. For instance, let's say we have x to the 8th power. The obvious way for a computer to do this would just be to multiply x by itself 8 times, and as you can see, that's going to require 7 multiplications. That's going to be pretty fast, but let's see if we can do it in fewer multiplications. Here's one method. We can do x times x equals x squared, and then we can multiply x squared by itself. Before, remember, we were just going to multiply by another x, but this time let's use x squared on both sides, and that's going to give us x to the 4th. And that's great because we've done just 2 multiplications. We skipped the x to the 3rd power, and we've been able to get to x to the 4th faster. And as you can probably see, we can just do this again. X to the 4th times x to the 4th equals x to the 8th. And that's what we needed. We just skipped x to the 5th, x to the 6th, and x to the 7th. We did this whole thing in just 3 multiplications. And so that's more than twice as fast as the original method. That's great. And also you can probably see that it's very easy to calculate powers of 2. If we wanted to get x to the 16th, then we would just square x to the 8th. And we could just square x to the 16th to get x to the 32nd, and so on. Now it's going to be really important later to know that it's easy to get to powers of 2. So what about things that aren't powers of 2? Let's look at x to the 15th. Now one way we can do this is we can do x times x equals x squared, and then we can do x times x squared to get x to the 3rd. Then we can square that. So we'll get x to the 3rd times x to the 3rd, which is going to equal x to the 6th. We can square that to get x to the 6th times x to the 6th equals x to the 12th. And then because we already have x to the 3rd and x to the 12th, we can multiply them together, and we're going to get x to the 15th. And it only took us 1, 2, 3, 4, 5 multiplications. So that's good. That's a lot faster than if we were doing x to the 15th the other way. That would have required 14 multiplications. The problem with this is that I used some tricks. Why did I multiply x by x squared and then start squaring x to the 3rd? And how would I know ahead of time that I could take x to the 3rd times x to the 12th? These tricks I use, I need a standard way to find those types of tricks. I need a way, an algorithm, that I can program a computer to follow so that it will instantly know what it needs to do to calculate any power. So to talk about this algorithm, which is called exponentiation by squaring, we're going to use a couple tricks of exponentiation, a couple properties. So let's say we have x to the power of a plus b. That's going to be the same as x to the a times x to the b. So why is this important? Well, let's look at an example. If we have x to the 5th, then because 5 equals 4 plus 1, our exponentiation property means that x to the 5th is going to equal x to the 4th times x to the 1, right? Now this is nice because x to the 4th and x to the 1 are both powers of 2, which, remember, are very easy to calculate. We can just keep squaring our results again and again. The problem with this is, how do we figure out what powers of 2 make up a number? I knew that 5 equals 4 plus 1, but what's the standard way to do that? Well, fortunately, binary is exactly what we need. A binary representation of a number is telling us which powers of 2 make up that number. So for instance, decimal 5, I'll write a D5 to show you I'm writing it in base 10, is going to be equal to binary 101. And that shows us that it's got 1, of 2 to the 0th power, 0 of 2 to the 1st power, and 1 of 2 to the 2nd power. Or it's got a 1 and it's got a 4, just like we showed up here. Let's look at another one. If we look at decimal 13, its binary representation is going to be 1 because it's got an 8, 1 because it's got a 4, a 0 for the 2's, and a 1 for the 1. So that's saying that 13 equals 8 plus 4 plus 1. Well, that's great, because now we can say that x to the 13th is equal to x to the 8th times x to the 4th times x to the 1. These are all powers of 2 that are very easy for us to calculate, so we just square to find those powers, and then we multiply together the ones we need. So let's look at that. We can do x times x equals x squared, then we can do x squared times x squared equals x to the 4th, then we can do x to the 4th times x to the 4th equals x to the 8th, and now we've got everything we need. We just multiply x to the 8th by x to the times x to the 4th, and then times x, and we get x to the 13th. Notice in this case we didn't need to multiply x squared in because there's a 0 right there in the binary representation of 13. So if you're wondering how many multiplications is this going to take, it's a little complicated because it depends on how many ones are in the binary representation of the number. But in general, the number of multiplications that are required is going to be fairly low, because if we double the number, it's only going to require one more multiplication, because every time we square it, we get the power that's twice as big. So let's look at, I made a program that shows us how many multiplications it takes in our original method and this new method, and it will graph it for us. And this code is going to be in the description, so you can play around with it yourself later. I'm just going to run it. So the blue line is how many multiplications the original method took, and the red line is how many multiplications the new method took. So x to the 1st power doesn't require any multiplications, x to the 2nd power requires one multiplication for both methods, and so on. Now something that you might be wondering is, it's kind of weird that the number of multiplications goes down from 7 to 8. Why is that? Well, let's think about the binary representation of 7 and 8. When we're doing x to the 7th power, 7, its representation in binary is 1, 1, 1. So we have to multiply together all those powers. But 8's binary representation is 1, 0, 0, 0. So we just have to square to get up to x to the 8th. We don't need to do any more multiplication, and that's why it went down. The other thing you might be wondering about is that this is kind of a complicated algorithm, at least compared to the original method, and it's only twice as fast when we're doing x to the 10th, because this requires 4 multiplications, this requires 9. That's true, but the critical thing is that as our exponent grows larger, this new method slows down much slower than the original method slows down. It actually slows down logarithmically. And the best way to show you how great that is just to graph it for a higher number. Let's go up to 100, graph it, and wow, look at that. We have, it goes up and down depending on how many ones are in the binary representation, but overall it's growing much slower than the other method, which means we'll be able to do some pretty huge exponents, and it's not going to be too expensive. Let's look at one more. Let's do up to 1,000. And look at that. It looks almost flat compared to the original method. It's growing so slowly. And that is really amazing. If you have an algorithm that can grow that slowly, then you'll be able to do huge operations very quickly. That's very important. Now you might be thinking, what might be a good way to code this? And I encourage you to code it on your own. That's a great way to solidify your understanding of an algorithm. There's a lot of ways you can do this. You could just calculate the powers by squaring each time, store them all, and then multiply together all the ones you need. I particularly like a recursive method of doing it. This is my Python code for doing the recursive method, and I'm going to also include this in the description. I think it'd be, if you want to learn more about this, a great way to start would be just using this code and looking at it and figuring out how it works. I hope that this video was helpful, and thanks for watching.